Good morning, I am Qwertyuioaedfggyhu Jr. This is our video about the theory of computation. The theory of computation is a field in computer science that explores the study of algorithms, models of computations, and their computational complexity. It delves into understanding what problems can be solved by algorithms and how efficiently they can be solved. The significance of the theory of computations lies in fundamental role in shaping our understanding of what can be computed and how efficiently it can be done. It provides a theoretical framework to analyze the capabilities and limitations of computing devices, aiding the design and optimization of algorithm and computational system. This understanding is crucial for various areas, including artificial intelligence, software engineering, cryptography, and computational biology, among others. Alonzo Church and Alan Turing were pioneering figures in the field of theoretical computer science and the theory. Alonzo Church, 1903-1995, was an American mathematician and logician. He is renowned for developing lambda calculus, a formal system for expressing computation based on functions and variables. Church's works on lambda calculus demonstrated that mathematical functions could be computed using a few simple rules. His contributions were foundational in understanding computability and the limits of what can be computed. Alan Turing, 1912-1954, was a British mathematician, logician, and computer scientist. He is best known for his concept of the Turing machine, a theoretical model of computation that laid the foundation for modern computer science. Turing machines help formalize the notion of an algorithm and computability. During World War II, Turing played a vital role in breaking German codes, using early electronic computers to aid and code-breaking efforts. Turing ideas were seminal in shaping the field of artificial intelligence and modern computing. Both Church and Turing made profound contributions to the theory of computations. Both Church and Turing made profound contributions to the theory of computation, which have had a lasting impact on computer science, mathematics, and related disciplines. Background: Church grew up in a scholarly environment as his father, Samuel Robbins Church, was a mathematician and educator. He demonstrated exceptional mathematical abilities from a young age, publishing his first paper at the age of 14. Education: Alonzo Church attended Ridgefield High School in Connecticut. He pursued his undergraduate studies at Princeton University, where he completed a degree in mathematics in 1924. Church continued his studies at Princeton for his graduate work, under the mentorship of Oswald Veblen. He completed his PhD in mathematics in 1927. During his graduate studies, he became interested in logic and its foundational questions, which significantly influenced his later work in the field of logic and computability. Alonzo Church's academic journey and research contribution, especially his work on lambda calculus and its impact on the theory of computation, have a lasting legacy in field of computer science and mathematical logic. Lambda calculus. Lambda calculus is a formal mathematical system invented by Alonzo Church in 1930. They study the fundamental concept and computability in functions. It's a notation system based on the use of lambda abstractions written as expression to define functions and function application. Lambda calculus operates on expressions, variables, and functions, allowing the representation of computation and algorithms. It provides a minimalist but powerful framework for expressing computation, making it a universal model of computation equivalent in power to Turing machines. Church showed that lambda calculus is capable of representing any algorithmic computation, establishing its significance in the theory of computation. Alonzo Church's lambda calculus laid the theoretical foundation for understanding the nature and limits of computation, influence developments in computer science, programming languages, and artificial intelligence. Lambda calculus is a formal system for representing and manipulating functions, providing a foundational framework for understanding computation. Here's an explanation of lambda calculus in the Number 1. Basic elements. Lambda calculus uses 3 basic elements: variable, example x, y, z. Lambda abstraction, expression and function application, example f, x. Variables represent inputs or parameters for functions. Lambda abstraction define functions by specifying how to transfer an input variable using a given expression. Function application applies a function to an argument leading to the evaluation of the function. Number 2. Lambda abstraction. A lambda abstraction as a form ax expression where x is a variable parameter and expression is the function body. Number 3. Function application. Function application is denoted by juxtaposing a function and its argument, for example fx. When a function is applied to an argument, the function body is evaluated by substituting the argument for the parameter in the expression. Number 4. Substitution and evaluation. Lambda calculus involves substitution of arguments to the function body based on the given lambda abstraction. Number 5. Example. An example lambda abstraction is ax x plus 1, representing a function that increments its argument by 1. Alonzo Church works particularly development of lambda calculus, established a profound mathematical basis for computation, and lead the groundwork for understanding computation in a formal and systematic manner. Here's a explanation of and his contributions. Formalized computation. Lambda calculus provide a formal and precise system for representing computation and mathematical functions using a simple notation based on lambda abstractions and function application. Number 2. Universal representation of function. Church demonstrated that lambda calculus is a universal model of computation, meaning it can represent any compatible function. Number 3. Equivalent to Turing machine. Church work established that lambda calculus and Turing machines were computationally equivalent. This finding, known as the Church-Turing thesis, implied that any computation that could be carried out by a Turing machine could be also expressed lambda calculus and vice versa. Number 4. Concept of effective compatibility. Church exploration of lambda calculus helped define the concept of effective Computability. A function is effectively computable if and only if there exists a lambda expression that represents it in the lambda calculus. Altogether, charge foundational contribution through lambda provides a rigorous mathematical framework for defining computation, understanding the limitation of computation. So, and establishing a basis for the theory of algorithm and computation, it leads the groundwork for the development of modern computer science, computational theory, and programming languages. That's all. Thank you.
Alan Turing, born on June 23, 1912 in Middle Valley, London, was a pioneer mathematician, logician, and computer science. He is widely regarded as one of the most influential figures in the development of theoretical computer science and artificial intelligence. Here an overview of Turing's background and early achievements. 1. Early life and education. Alan Matheson Turing was the second of the two sons born to Julius Matheson Turing and Ethic Saraton. His father was in the British India Civil Service, and his mother was an active member of the Women's Social and Political Union. Turing attended the Sorbonne School, prestigious boarding school in Paris, and showed exceptional aptitude in mathematics from an early age. 2. Education at Cambridge University. In 1931, Turing entered King's College, Cambridge, where he studied mathematics. He graduated in 1934 with a first-class degree in subject. During this time, he was exposed to foundational mathematical idea and logic that would shape his future work. 3. Turing machine and compatibility theory. In 1936, Turing published in seminal paper on compatible numbers in which application to the historic problem, where he introduced the concept of theoretical computing machine known as the Turing machine. This theoretical device provides the foundation for modern computer science and compatibility theory. Demonstrate that certain problems are fundamentally unsolved by computers. 4. Work on Princeton University. After completing his study at Cambridge, Turing went to Princeton University in the United States to study under Alonzo Church. During his time at the Princeton, he further developed his idea on compatibility and collaborated with others prominent mathematician and logician. 5. Civilized during World War II. During World War II, Turing played a crucial role in British Park, the British Code Breaking Center. He was instrumental in breaking the German Enigma Code, which he significantly contributed to the Allied victory. Turing work on code breaking demonstrated his exceptional analytical and problem-solving abilities. automatic computing machine. In 1945, Turing presented a report titled Proposed Electronic Calculator, in which he outlined the design of a store program computer, now known as the Automatic Computing Engine (ICE). His design and concept were influential in the development of modern computer. 7. Turing test and artificial intelligence. In 1950, Turing published a paper titled Computing Machinery and Intelligence, where he introduced the Turing test to determine a machine's ability to exhibit intelligent behavior equivalent to or indistinguishable in guide from the of human. This work led the foundation for field or artificial intelligence. These are the another idea for what Alan Turing early achievement revolutionizes the field of computer science, laying the groundwork for the development of modern computer, computation theory, and artificial intelligence. Despite his remarkable contribution, Turing faced personal and positional challenge, including persecution for his homosexuality, led to his tragic death in 1954. However, his legacy continued to inspire and influence the field of mathematics, computer science, and artificial intelligence to this day. Alan Turing's seminal paper, titled on computable numbers with an application to the incident problems, was published in 1936. In this paper, Turing introduced two fundamental concepts that revolutionized the field of theoretical computer science: computable numbers and Turing machine. Computable numbers. Alan Turing seminal papers, titled on computable numbers with an application to the incident problem, was published in 1936. In this paper, Turing introduced two fundamental concepts that revolutionized the field of theoretical computer science: computable numbers and Turing machine. Computable numbers. Turing began addressing the fundamental question in the nasipyat na sad. Alan Turing seminal paper titled on computable numbers with an application to the incident problem, was published in 1936. In this paper, Turing introduced two fundamental concepts that revolutionized the field of theoretical computer science: computable numbers and Turing machine. Computable numbers. Turing began addressing a fundamental question in the foundation of mathematics, known as the incident problem, decision problem, which was posed by mathematician David Hilbert and Wensley Ackermann. The problem essentially asks for an algorithmic method to determine the true or falsity of any mathematical statement based on formal state on excess. Turing machine. Turing introduced the theoretical concept of a Turing machine as a model of computation. A Turing machine is an abstract mathematical device that concept of an infinitely long tape, a read-write head, and infinity set of states. The tape of divided into cells, each of which can hold a symbol from infinity alphabet. Kadagdagang idea about sa this concept we groundbreaking because they provide us a piece of formal definition of computing and computable Turing. Formulated of the Turing machine become a fundamental theoretical concept in computer science, serving as a basis on understanding the limit on capabilities of what can be computed by a machine. It also provides a theoretical framework for discussing the feasibility and solvability of mathematical problems, leading to significant advancement in the theory of algorithmic and compatibility. Turing machine and fundamental and abstract computational device that serve as a theoretical foundation for understanding computation and algorithm introduced by Alan Turing. In 1936, the Turing machine is a simple yet powerful mathematical model that helps analyze the limits of what can be computed. Alan Turing machine consists of the following components. Tapes. The tapes in an infinitely long sequence of cells, each of which can hold symbols from infinite alphabet. The tape extended infinitely in both directions. 2. Read, write, and head. The read-write head is positioned over a single cell on the tape at any given time. It can read the symbol currently under the head and write a new symbol onto the tape at the position. 3. Finite state control. The finite state control is a finite set as a state that the machine can be in. It determines the machine behavior based on the current state and the symbols being read. The Turing machine operates based on a set of transition rules that define how it behaves at each step. Each transition rules specify the following action. Read the symbol current under the head. Write the symbol to be written on the tape and the current position. Move the head one position to the left, L, right to the R, or stay in the same position in next state. Transition to a new state. The machine starts in an initial state and follows the transition rules based on the current state and the symbol in reads. It's performed that specific action and transaction to a new state accordingly. This process continues until the machine reaches a designated halting state, at which point it stops. A Turing machine can perform various tasks, and its behavior is defined by the transition rules, which is effectively encode the algorithm and computing to the carry out. It can simulate an algorithm or computing that can be described in a systematic step-by-step manner. The concept of Turing machine is crucial in theoretical computer science because it allows for the analysis of computability and decidability of problems. It helps establish what problem can be solved algorithmically and what problems are beyond the reach of computing. The Turing thesis asserts that any function that can be effectively computed can be computed by a Turing machine, reinforcing the significance of Turing machine in defining the boundaries of computation. That's all. Thank you.
So this is the comparison of lambda calculus and Turing machine. Lambda calculus and Turing machines are distinct formal systems used to describe computation. Lambda calculus focuses on function manipulation using abstraction and applications. It uses lambda expression to represent function and applies them to arguments through a substitution-based approach. Turing machine, on the other hand, focuses on abstract computation through a tape-based mechanism. The read and write symbols on an infinitely long tape based on transition rules defined by a state machine. Despite their different approaches, both lambda calculus and Turing machines are equivalent in their expressive power and can compute the same class of compatible function. This equivalence is known as the Church-Turing thesis, demonstrating that any computation that can be performed by a Turing machine can also be expressed in lambda calculus and vice versa. The Church-Turing thesis posits that any effectively calculable function can be computed by a Turing machine. This hypothesis was independently formulated by Alonzo Church using lambda calculus and Alan Turing. Through his conceptualization of Turing machines, despite originating from different formalization of computation, that Church-Turing thesis unifies these approaches by establishing their equivalence. Any computation feasible in one formal system can be effectively represented in the other, underscoring the fundamental concept of compatibility. Church and Turing foundational contribution revolutionized the theory of computation and greatly influenced computer science. Alonzo Church, lambda calculus, and Alan Turing machines lead to theoretical groundwork for modern computer science. They provide a formal framework to define computation and compatible function, paving the way for understanding the limits and capabilities of algorithm. Number 1. Theory of computation. Church and Turing works established a solid theoretical foundation leading to the theory of computation, formal language, automata theory, and complexity theory. Number 2. Compatibility and decidability. Their contributions help define what can and cannot be computed, forming the basis for understanding compatibility and decidability. Programming language. Lambda calculus inspired the design of functional programming languages, while Turing machine influenced the architecture and design of actual computers. Number 4. Algorithms and complexity. The understanding of compatible function and complexity classes has led to the development and analysis of efficient algorithms, a cornerstone of computer science. And that's all. Thank you.